Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Digital Signal Processing Part 2 from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the third important process of sampling, that is quantization of continuous amplitude signals. Second, we will discuss about the quantization errors. Thirdly, the coding of quantized samples will be discussed. Next, we will discuss about the very important component, that is digital to analog converter. Then we will discuss about the finite duration impulse response FIR and infinite duration impulse response IIR. Recursive and non-recursive discrete time systems will also be discussed. Lastly, linear time invariant systems, which are characterized by constant coefficient difference equations, will also be discussed in detail. So students, let us start with a basic introduction about the module. Since a discrete signal has discrete points in time, but still has continuous values in amplitude, so the amplitude of the signal must be discretized in order to store it in digital format. So the values of the amplitude must be rounded off to discrete values. So if the vertical axis is divided into small windows of amplitudes, then every value that lies within that window will be rounded off or quantized to the same value. So for example, consider a waveform having a window size of 0.5 volts, starting at -4 and ending at +4 volts. So at a discrete point in time, any amplitude between 4 volts and 3.5 volts will be recorded as 3.75 volts. In this example, the center of each 0.5 volt window or quantization region was chosen to be the quantization voltage for that region. So in this example, the dynamic range of the signal is 8 volts. Since each quantization region is 0.5 volts, so there are 16 quantization regions included in the dynamic range. It is important that there are 16 quantization regions in the dynamic range, since a binary number will represent the value of the amplitude. So it is important that the number of quantization regions is a power of 2. So in this example, 4 bits will be required to represent each of the 16 possible values in the signal's amplitude. So let us now study first the quantization of continuous amplitude signals. So the process of converting a discrete time continuous amplitude signal into a digital signal by expressing each sample as a finite number of digits is called as quantization. Let XQN denotes the sequence of quantized sample at the output of quantizer, that is XQN equal to Q of Xn. So the error introduced in representing the continuous valued signal by a finite set of discrete value levels is called as the quantization error or quantization noise. Hence, quantization error is the difference the quantized value and the actual sample value, which is represented by EQN equal to XQN minus XN. So let us take an example. Consider the discrete time signal as xn equal to 0.9 to the power n for n greater than equal to 0, and it is 0 for n less than equal to 0, where n is the significant digits cannot processed by calculation. So let we want one significant digit to eliminate the excess digit, that is truncation or rounding. This implies XQN, which is shown in this figure. The values allowed in the digital signal are called as quantization levels, whereas the distance delta between the two successive quantization level is called as the quantization step size or resolution. So the rounding quantizer assigns each sample of xn to nearest quantization level. The quantization error EQ. Now here n is limited to minus delta by 2 to plus delta by 2. So students, this table shows the different values of xn for different values of n, then xqn after truncation, then xqn after rounding off, and the error for the quantization error, that is the difference between xqn minus xn. If xmin and xmax represents the minimum at the maximum values of xn and L is the number of quantization levels, then delta equal to xmax minus xmin divided by L minus 1. So if L increases, delta decreases, which implies quantization decreases and accuracy increases. So students, this figure shows the summary of the sampling and the quantization of a sinusoidal signal, where we have the unquantized samples, which are represented by XANT. Then we have the original analog signal XAT, then quantized samples XQNT. And delta is the quantization step, and all these levels are represented by the quantization level. Analysis of quantization error. So now students, the quantizer system, the block diagram is represented by this. If the input is xn, we get the output as xqn. And mathematically, we can represent it like this, that is xn as the input, summation, and eqn is the error, which gives us the output as xqn equal to xn plus eqn. So to carry out the analysis, we make the following assumptions about the statistical properties of EQN. So here the error EQN is uniformly distributed over the range minus delta by 2 to plus delta by 2. So the error EQN and the error EQM for m not equal to n are uncorrelated, and the error sequence curly bracket EQN is uncorrelated with the signal sequence xn. Signal sequence xn is zero mean and stationary. The mean square error PQ is PQ equal to 1 by 2 tau multiplied by integral minus tau to plus tau EQ square t dt equal to 1 by tau integral 0 to t EQ square dt, where tau denotes the time that XAT stays within the quantization levels. So this figure shows the delta and the variation of EQT with t. Since EQT equal to delta by 2 tau multiplied by t, now here t is varying from minus tau to plus tau, we have PQ equal to 1 by tau multiplied by integral 0 to tau divide over delta by 2 delta square t square dt, which is equal to delta square by 12. So if the quantizer has 8 bits of accuracy and the quantizer covers the entire range 2a, the quantization step is delta equal to 2a by 2 to the power b. Therefore, PQ equal to a square by 3 divided by 2 to the power 2b. So, the average power of the signal is Px equal to 1 by tau p, Tp, the integral 0 to Tp over a cos omega naught t the whole square dt equal to a square by 2. So the quality of the output of A to D converter is usually measured by the signal to quantization noise ratio SQNR, which provides the ratio of the signal power to the noise power. That is XQNR equal to Px by Pq equal to 3 by 2 multiplied by 2 to the power 2b, and in decibels it is represented by SQNR in decibels equal to 10 log SQNR equal to 1.76 plus 6.02 b. So let us now discuss about the coding of quantized samples. The coding process in the A to D converter assigns a unique binary number to each quantization level. That is, if we have n L levels, then 2 to the power b will be greater than equal to capital L, where b is the number of bits in words. So, which implies b must be greater than equal to log 2L. So, the number of bits required in the coder is the smallest integer b greater than or equal to log L. If we have a word length of b plus 1 bits, we can represent 2 to the power b plus 1 distinct binary numbers. Hence, b plus 1 must be greater than equal to log L. Then the step size or the resolution of A to D converter is delta equal to R by 2 to the power b plus 1. So as your b increases, higher sampling speed and finer quantization, that is your delta, decreases. So more expensive will be the device. So let us now discuss about the digital to analog converter. D2A conversion is usually performed by combining a D2A converter with a sample and hold SH followed by a low pass filter, which is shown in this figure, where a digital input signal is applied to the D2A converter and then to the sample and hold circuit and then to the low pass smoothing filter, and finally we will get the analog output signal. Now here there is one more important factor is there, that is the settling time, which is nothing but the time required for the output of the D2A converter to reach and remain within a given fraction of the final value after the application of the input code word. The sample and hold SH approximates the analog signal by a series of rectangular pulses whose height is equal to the corresponding value of the signal pulse. So this figure shows the response of the sample and hold. As shown, the approximation is basically a staircase function which takes the signal sample from the D2A converter and holds it for t seconds. So when the next sample arrives, it jumps to the next value and holds it for t seconds and so on. So we have already studied the LTI systems in terms of HN. So it is convenient to subdivide the class of LTI into two types. that is your finite duration impulse response FIR and infinite duration impulse response IIR. FIR system has an impulse response that is 0 outside of the some finite time interval, that is Hn equal to 0, n equal to 0 and n is greater than equal to m. So the convolution formula for such a system reduces to yn equal to summation over k equal to 0 to n minus 1 over hk x n minus k. So here yn is simply a weighted linear combination of input samples x n minus k, where weights by the values of impulse response hk. So hence we say that FIR systems has a finite memory of length m samples, involving addition, multiplication and a finite number of memory locations. FIR system is implemented directly as implied by the convolution summation. So the IIR LTI system has an infinite duration impulse response. So in the output based on the convolution formula, that is yn equal to summation of hk x, the convolution xn minus k, where causally has been assumed to be k greater than 0. So we say that IIR system has an infinite memory. So this equation involves the infinite memory locations, multiplications and additions. We can realize IIR system using others means, that is by using difference equations, which is practically and efficiently computationally. So this is very useful for the implementation of digital filters and modeling of physical systems and phenomena. Recursive and non-recursive discrete time systems. The system in which the output yn is a function of several past output values and present and past inputs is called as the recursive system. Thus, the output of a causal and practically realizable recursive system can be expressed as yn equal to f of yn minus 1, yn minus 2 and so on till yn minus n, capital N, comma xn, xn minus 1 and so on till xn minus m, where f denotes some function of its arguments. Now we can represent this by mathematically, that is xn is applied to f of the f operator and we will get yn, which is fed back through z minus 1 to again this f operator. So we wish to compute the average cumulative average of the signal xn in the interval 0 less than equal to n, as yn equal to 1 by n plus 1 multiplied by summation over k equal to 0 to n xk. Now here n is equal to 0, 1, 2, etc. And here yn requires the storage of all the input samples xk. For k0, k is varying from 0 to n. Since n is increasing, our memory requirements grow linearly with time n. However, yn can be computed more efficiently by using previous output value yn minus 1. So from this previous equation, we have n plus 1 multiplied by n equal to summation over k equal to 0 to n minus 1 over xk plus xn equal to n by n minus 1 plus xn. Now where we have replaced n by n minus 1. So yn can be written as n by n plus 1 yn minus 1 plus 1 by n plus 1 xn. Therefore, cumulative average yn can be computed recursively as n by n plus 1 multiplied by yn minus 1 as the previous output value and 1 by n plus 1 and xn, this is the present input. So that is the 2 multiplication, 1 addition and 1 memory location, that is yn minus 1. So coming back to the recursive system, let us consider an example which is represented by the following, that is yn equal to n by n plus 1 multiplied by yn minus 1 plus 1 by n plus 1 multiplied by xn. So this is representing by the following block diagram, where xn is the input to the summation and then it is applied to the multiplication, which is done by 1 by n plus 1, and then we get the output which is fed back to z minus 1, then fed to the multiplication with n and then to the xn. So equation 3 has time variant coefficients, that is input-output equation for a linear time variant system. In contrast, if yn depends only on the present and the past inputs, then yn equal to f of xn, xn minus 1 and so on till xn minus m. So such a system is called as a non-recursive system, which is shown mathematically in the figure below. So let us take an example, that is the convolution summation for a causal FIR system is given by yn equal to summation over k equal to 0 to m over hk multiplied by xn minus k, where this multiply is the convolution, equal to h0 xn plus h1 xn minus 1 plus so on plus hm xn minus m. So this is represented by the f operator which is acting on xn, xn minus 1 and so on xn minus m. Hence, the causal linear time invariant FIR systems described by the above formula are non-recursive. Let us now discuss the linear time invariant systems which are characterized by constant coefficient difference equation. Students, suppose that we have a recursive system with an input-output equation as yn equal to yn minus 1 plus xn. That is a first order difference equation, and here a is a constant. So the block diagram is given by this figure, where xn is the input to the summation and then we'll get the output yn, which is fed back to z minus 1, and through a it is fed to the input. So the input-output relation, called as the difference equation with constant coefficients, and is the input-output equation for a linear time invariant system. So if we compute the successive values of yn for n greater than 0, then equal to 0, basically beginning with y0, let us apply an input signal xn to the system for n greater than equal to 0. So we have y0 will be equal to a y minus 1 plus x0, y1 equal to a y0 plus x1 equal to a square y minus 1 plus a x0 plus x1, y2 equal to a y1 plus x2 equal to a cube y minus 1 plus a square x0 plus ax0 plus ax1 plus x2, and so on. So we have this yn will be equal to a(yn minus 1 plus xn, which is equal to a to the power n plus 1 y minus 1 plus a to the power n x0 plus a to the power n minus 1 x1 plus so on plus xn, or yn equal to a to the power n plus 1 y1 due to initial condition plus summation over k equal to 0 to n a to the power k x and k, which is nothing but response to the input signal xn. Now here n is greater than equal to 0. If the system is initially relaxed at time n equal to 0, then y minus 1 is equal to 0. That is the output of the delay. So memory should be 0. Thus, a recursive system is relaxed if it starts with 0 initial conditions. This system is at 0 state and its corresponding output is called as the 0 state response, and it is denoted by yzsn, which is given by yzsn equal to summation k equal to 0 to n over a to the power k xn minus k, where n is greater than equal to 0. Thus, relaxed recursive system, which is given by equation 4, is LTI-IIR system with Hn equal to a to the power n un. Y minus 1 equal to 0 indicates that input signal can be assumed causal. Therefore, upper limit is n because xn equal to minus k equal to 0 for k greater than n. This is a convolution sum involving the input signal xn convolved with impulse response hn equal to a to the power n un. So let the system, which is given by equation 4, is initially non-relaxed. That is, y minus 1 is not equal to 0 and xn is equal to 0 for all values of n. Then the output of the system with 0 input is called as the 0 input response or natural response, which is denoted by yzin. So yzin will be equal to a to the power n plus 1 y minus 1 n greater than equal to 0 with xn equal to 0. So recursive system with non-zero initial conditions y minus 1 not equal to 0 is non-relaxed and produces an output without being excited. That is, xn equal to 0 due to memory of the systems. Total response of the system is yn equal to yzs, that is a forced response due to xn, plus yzin, that is a free response or the natural response, depend on the nature only. Hence, the general form of the possible recursive system, which is described by linear constant coefficient difference equation, yn as the current output equal to minus summation over k equal to 1 to n, ak yn minus k, that is a past output, plus summation over k equal to 0 to m, bk xn minus k, past and current input, or summation over k equal to 0 to n, ak yn minus k equal to summation over k equal to 0 to m, bk xn minus k, a naught equal to 1. N orders of difference equations, or the order of the system. There is a negative sign in equation 8, that is due to convenience. So equation 8 represents the output of the system, a time t, as weighted sum of past output as well as past and the present input signal samples. So in order to determine yn for n greater than equal to 0, we need xn for all n greater than equal to 0 and initial conditions y minus 1, y minus 2, so on, y minus n. We need to know about the past history of the response of the system to compute the present and the future outputs. So a system is linear if it satisfies the following three requirements. Number 1, the total response Yn should be equal to Yzin, that is the zero input response Xn, plus Yzs, zero state response Y minus 1. So, the second one is the principle of superposition, which applies to zero state response. And the third one is the principle of superposition applies to zero input response. That is, for a relaxed system, Yzin should be equal to 0 because Y minus 1 equal to 0. Thus, condition 2 is sufficient. So, let us now consider an example where we need to find Yn, that is for n greater than equal to 0, of the system given a specific input xn, n greater than equal to 0, and the set of initial conditions. So we need to find out the solution of the linear constant coefficient difference equations. The total solution of the sum of the two parts, that is Yn equal to Yhn, that is the homogeneous or complementary solution, plus Ypn or the particular solution. So the homogeneous solution of a difference equation, we consider the following homogeneous difference equation, that is summation over k equal to 0 to n of ak yn minus k equal to 0. So assuming the solution of the form similar to that of solving a linear constant coefficient differential equation, we assume that solution is in the form of an exponential, that is Yhn equal to lambda to the power n, which is the equation 11, and substituting this equation back in equation 10, we have summation over k equal to 0 to capital N ak lambda to the power n minus k equal to 0 and E0 is equal to 0. So H is for the solution to the homogeneous difference equation, that is lambda to the power n minus capital N multiplied by lambda to the power n plus a1 lambda to the power n minus 1 plus a2 lambda to the power n minus 2 and so on, plus an minus 1 lambda plus an equal to 0. So characteristic polynomial of the system is, in general, it has n roots, where which we denote it as lambda 1, lambda 2 and so on and lambda n. So let all the roots are distinct, then most general solution is Yhn equal to c1 lambda 1 to the power n plus c2 lambda to the power lambda 2 to the power n plus c3 lambda 3 to the power n plus so on plus cn lambda n to the power n. So these coefficients are determined by putting xn equal to 0, that is a zero input response of the system, and initial conditions. So students, let us summarize what we have learnt in this module. First, we discussed about the quantization of continuous amplitude signals. Secondly, the analysis of quantization errors was done in detail. Coding, which is a very important thing in order to have a discrete time system or discrete signal processing, that is the coding of the quantized samples. Next, we discussed about the digital to analog converter. Next, that is two important kind of systems were discussed, that is finite duration impulse response FIR and infinite duration impulse response IIR. Recursive and non-recursive discrete time systems were discussed along with their mathematical description. Lastly, we discussed in detail about the linear time invariant systems, which were characterized by constant coefficient difference equation, and we discussed it with a particular example. Thank you.